Yeah, thank you. Good morning, everyone. Welcome to third day, fifth lecture on organic solar cell. This lecture actually originally planned for talking about OFET, organic field effect transistor. Since yesterday evening we saw that some of the working principle of organic semiconductor mechanism. Just to make a continuity, I'm doing just to continue the organic solar cell, and I said some of the devices how we can make efficient organic photovoltaic that we have seen yesterday, the excitonic process. That's more or less the same process going to happen here. So to make the continuity, I'm doing this one. The OFET one, we can do it tomorrow afternoon session. Okay. So in this lecture, I'm coming after the photophysics because the photophysics and excitonic process is linked to the next topic. So we'll continue that. So in this topic, what I'm going to do is I just recap some of the slides which we have seen yesterday. That is very important to understand the following topic, and also tell you about what is the progress happened the last 10-15 years. I won't tell much about what is happening in 10 years before, mainly concentrating only on important points which is necessary to have a very good device fabrication purpose. So what are all the technique we used? That's important. So yesterday I talked about everything is not only one factor, it's interplay of multiple factor to make a good cell. Okay, we have seen how to design a good organic semiconductor. So that's the one part. After using the organic semiconductor, then we define the property, energy levels, how to determine the energy levels that we have seen. After suitable energy level, after selecting the material with the suitable energy levels, then we incorporate into the device in terms of what device architecture we are going to take, and also what device interface layer, and also what is a contact at the same time, what is a donor acceptor combination we are going to take. That's also very important. And when you have the mix it, in what ratio we are using, and what the solvent we are going to use, and what is the thickness of the film we are going to make, because thickness is a very important factor which affects the performance of this OPV device. OPV means organic photovoltaic. Okay, I will use the term this OPV, and throughout the lecture you can understand organic photovoltaic short form is OPV. Okay, and then I'll talk about some of the optimization technique. When you have the optimization technique, if you remember from yesterday lesson, from yesterday lecture, I told that getting bulk heterojunctions, making bulk heterojunctions concept, this architecture is very important, because if you remember the excitonic, the exciton can able to diffuse only 15 to 20 nanometer. It should meet the heterojunction within this distance, 20 to 30 nanometer. That's why your donor acceptor phase should be within 20 to 30 nanometer. So we have to control this morphology. Okay. So what is the technique is available to optimize to morphology? There is not single technique. There is multiple techniques. Those technique I'm going to talk about these things. So those techniques developed in different period over the last 10 to 15 years. I'm putting this together so that you can easily understand what all are. I'm saying only important thing. I can't say all the technique. I'm going to talk about only the important aspect of device fabrications. Okay. If you have any questions at the end of the lecture, you can ask me. Now let us go to the section. Just to recap. This one, why you want to do that? We know that yesterday we went through these slides. I want to show that where we are moving from, starting from this block, red dot is organic photovoltaic, starting from 3% from 2001 to now it's going up to close to 20%. And then the basic device, this one I have seen that initially when the device started is only the bilayer, like same as silicon cell, we have donor layer and acceptor layer, we have only one heterojunction. Since I said this exciton only diffuse to few nanometer inside the donor phase, we need to make that this donor is very, very thin. Then only this exciton should reach the interface and get dissociated and get charge separated. That's why this device works well. When you have the very thin layer means 20 to 30 nanometer, this very, very thin layer. So that limit, whenever the layer is very thin, your absorption will be limited. Then the charge generation will be limited. Then the current generated from the charges is also limited. The performance very low. Of course, if you want to improve this performance, we need to have a little bit thick layer so that we can absorb more photon and generate more charge carriers and more current we can generate. So how to improve that? That's why we have started this other, and also they said we have the charge transfer process very fast. Okay, as I said, this one you can see this block diagram and exciton generator. After that, it will go to that interface. It will get okay. And the light falling on this one, then it will exit on generator. After that, at the interface, it will get separated, the charges. So like this things. This is very small pictorial things. Okay. So because of this bilayer is limited, because of the very short exciton wavelength, the bulk heterojunction is started. As I said yesterday, the bulk heterojunction is nothing but mixing of two donor and acceptor solutions. Here we mix together so that this will uniformly distribute the heterojunction over all the active layer, because in previous case donor we have one heterojunction. Here we can have a multiple heterojunction so that exciton can easily, within the short distance, it will go to the interface and get dissociated. Then we can get more charges generated. That's a bulk heterojunction. And this bulk heterojunction is giving a very good solution to solve that exciton diffusion length issues. Okay, and so that the exciton reach interface, and so that the charge can be separated in the domain itself. Okay, this also we have seen yesterday, and also I said how to make it fabricate. I'm giving the overall view how to fabricate the simple cell. So this is the one. This is a simple device architecture where we have a ITO means is a indium tin oxide. Indium tin oxide, why we are taking it? Because if you want to use a solar cell, one side should be, the light should pass through. That means one side the light should be transparent. That's why this ITO is a transparent electrode. We choose electrode. Of course, the top electrode is aluminum. Aluminum is completely opaque. Okay, the top surface is opaque one. The bottom is transparent. Okay, on the ITO we quote it as P dot PSS. P dot PSS is a short form of polyethylene dioxythiophene, and PSS polysulfonated type. The chemical structures are given here. We coat very thin layer of P dot PSS. If you say this thickness around 20 to 25 nanometer, this is known as a whole transport layer. Whole transport, we can call whole transport layer, which the energy levels is favorable to extract the holes from the active layer. And calcium is a very low work function metal. It will easily extract the electron from other side. So normally to extract the electron, for electron transport we use a low work function, and for hole transport we use a high work function. Okay, so the ITO together with the P dot, the work function high means it gives around 5.2. This is 5.2, and the LUMO levels, the calcium is around 2.8, 2.5. It's very high. So that's why it gives the good built-in potential and get charges separated out. Okay, so we quote this P dot PSS on top of ITO. So this is I'm giving the example of the indium tin oxide. You see on the glass substrate, you can see some of the pattern. So this is when you have the device, right? We need to have some patterned ITO, because the ITO is everywhere. Then we have on top of that we have to coat on aluminum as well, so that we do some type of patterning. That means we can have this is ITO, this middle line, so that when you coat, then after coating all layer, then top we will put a silver or aluminum. So those layer will it will come as a like crisscross, so that where is the junction of your ITO and the silver, that's the working active area. That's called as active area pixels. We have different pixel we form. This is a lab scale device. When you have the large area device, we can have the big printable large scale and big substrate we do. But laboratory scale we define ITO like this. So on top of this ITO, after doing cleaning process, we do P dot and using the spin coater at high speed. Then after that we do the annealing process, because this P dot is in a water based solvent, it dissolves in water. So once it makes spin coated, after making 150 degree we will dry the P dot so that water will go out. So after coating the P dot, we use this P3ST PCBM. I said just one example. actually we can use any mixer, if any new material, okay, but donor acceptor, anything, and mix it together with any solvent. Now currently mostly people are using chloroform is a very good solvent, but toluene, but which is not good for industrial purpose, and toluene or xylene is another solvent people use, though some of the materials can dissolve in toluene as well. So any solvent we will dissolve these things. Then on top of PDOT we coat this P3ST PCBM. After coating this 2 layer, then next step is we use calcium or aluminum. So this step we have to do is at thermal evaporation, that we need to get into the vacuum, and the calcium and all is a very high melting point. Then we have to do it in a high temperature vacuum and make it a vapor, and the vapor will deposit into the surface. Okay, but now we have replaced this calcium with the different type of organic layer, that also we can spin coat. This layer also, there is I'm going to talk about what we are doing in interface engineering. We can use either aluminum we can evaporate, and in addition alternatively we can do the silver paste, where we can also print silver paste as well for the final purpose. But laboratory scale we want to get the best out of it, that's why we are doing all those in thermal evaporation conditions. Okay, so this is a full fabrication process normally. Anyway, some of the things may be different. Basically this one, we need to have one cold transport layer, one electron transport layer, and one transparent metal electrode and top metal electrode. So these are all 1, 2, 3, 4, 5 layers is essential for any device to work. Okay. Okay, I am giving what is the different combination of donor acceptor. I said the main thing, the efficiency will depends on what is a photoactive layer, where all the charges are generated upon excitation, upon irradiation. So this is polymer PCBM is Fullerene type acceptor. This is a different type of combination of material we can take. One is polymer PCBM, another one is polymer donor and polymer acceptor. There is another combination. And polymer, and people sometimes they use cadmium selenide nanocrystal, it's quantum dot we can use. This all are N type material. And polymer and metal oxide nanocrystal also use. Metal oxide mean we can take N type metal oxide like zinc oxide or TaO2, that type we can mix. The other thing is small molecule polymer. Small molecule donor we can take, polymer acceptor we can take, and also small molecule. So this type of various three combination we can take. So some of the example I have taken, this is a polymer for donor material, and these all things are polymer. So these are all small molecule CPC. Then this is a Fullerene acceptor, and these are all small molecule non-Fullerene acceptor. This is Fullerene, this is non-Fullerene acceptor, and these are all things. Okay, this is a different type of combination we use in the OPV devices. Okay. So this is a very first device which published in 2003. That time is performance is 3.5. You see that standard architecture is started in 20 years before is PDOT PSS P3HT PCBM calcium. This is a very classic donor material. People used to good performance using this combination of material, because you know that C60, the PCBM, is a very spherical molecule, very spherical one, so that wherever it will assemble, it will have a very nice crystalline structure, because if the PCBM is assembled anyway, it looks like crystal because it's a spherical one. Spherical whenever it is joined, that it will be crystalline one. If it is different architecture only, we can have either crystalline if it is a favorable pi stacking. If not, it may be self-assembled into different type of orientation, so it will be more amorphous piece. But in case of PCBM, it always make very well crystalline acceptor phase. So that this type of material works well. If not so great, at least the good working device we can find out how is the fill factor. You know, yesterday I talked about what is fill factor. Fill factor means when you get a JV curve, how good the fill factor, how good the squareness of the JV curve from short circuit to open circuit. If it looks like square, the device is very good you are making. If not, there should be a lot of recombinations happen that we need to address. Okay, that we can do it by how we good optimize the optimization to make the good devices. Okay. So this is the very first device. You see, the EK we are getting that time is close to 70%, 0.7. This is one of the first one. So from after that, from 2003 and 2000 until 15, we got a efficiency improved up to close to 10% only. So in 10 years time, we improve the device from 3%, not 10 years, 12 years time, only 3% go up to 10%. That time they used polymer is PTP70H. This one of the another, this is donor acceptor polymer. If you remember in our organic semiconductor design, I talk about donor acceptor, the push-pull effect also one of the criteria to make this organic semiconductor. So this is one of the example of donor acceptor. They call this a copolymer. When you are using the donor acceptor adjacent one, this is called a copolymer, donor acceptor copolymer. Okay. So this polymer is gave a very good fill factor. So here what they did is they just find out with adding different proportion of your acceptor PCBM and just to check in the device, the same architecture here. So here they use something inverted architecture. Inverted architecture means next slide I will go through what is regular and inverted one. So inverted one means in the bottom side, the previous one we extract holes and top is electron. In this case, the bottom we extract electron, top is hole. Everything is inverted. So how we do that? Just we change the work function of the bottom electrode and change the different work function interlayer. By just changing the interlayer, we can change the device architecture. So how we can do? This everything is used what material we are using and which material we have to use to make it inverted or regular architecture. We are going to see that. Okay. So in this case, by varying the PCBM at different ratio at 10, 20, 30, 51, we can see the at least the variation. You can see the variation in JSC because at optimum the blend ratio of around 65, I think there we can get a best 10.61. With the 65 means the percentage 65 remaining 35 is your donor material is around 1:1.5 or things. If you did that one portion is your donor and the remaining 1.5 is acceptor. In that ratio it works well. And this is optimization because as I said initially, the composition of donor acceptor ratio also is one of the important criteria to get a good cell. So this is one of the example. We have to use the right combination of donor acceptor. Okay, whenever you get any new material, this is one of the point you need to consider to make a device, different ratio of donor and acceptor. Okay. Other thing is, okay, now at this stage, the problem is all the donor molecule will get only absorbed is around less than 800. Suppose less than 800 means if you want to improve the short circuit current, that's a main contribution to give the high performance. Short circuit current is one of the criteria. If you see the efficiency depends on your short circuit current, open circuit voltage and fill factor. These three things only will give the good power conversion efficiency. I say it's a PCE. So one of the thing is we need to improve the short circuit current. How to improve that? If you want to improve the short circuit current, you have to improve the absorption, the range. It should have the extended absorption of sunlight. Okay, it have a wide solar radius, solar energy harvesting. So far before that, all the donor material will absorb only 800. So if you want to improve the EQE, you have to extend this 800 to further, so that, and also we have to extend to enhancing EQE as well. So when improving these ones, we can improve the power conversion efficiency of these devices. And also, as I said yesterday, the other parameter is VOC. How we can improve the VOC? We need to maintain the energy levels. Energy level means the VOCs depends on the donor HOMO and LUMO of acceptor. That we need to adjust to get the right VOC. So, and the second thing is molecular. Second thing is device geometry. I will going to talk about what are all the different device geometry available to make the devices. That is, I said right just now, there are regular geometry, there are inverted geometry. The third one is the tandem geometry. Tandem device, we can do multiple devices in one stack. Okay, that's standard. There are three types of things are available. The third one is interface engineering. Interface engineering we are going to deal in the last class. We are going to see in detail. But now we are going to see the morphology control is very, very important. As I said in the start of this lecture, how to get the optimum morphology of the nanoscale bulk heterojunction concept. We need to have with the phase separation of 20 to 30 nanometer, how we can. That's a very important point. there are various options available. One is choice of solvent. So by choosing which solvent we are dissolving the material, that makes your morphology different. The second one is a thermal annealing. Yesterday when you make a P3S cell, if you are watching that, when you coat it, it was only the some blackish purple color. After annealing, you can see that it completely turned to red color. That one you can say that there is a structural arrangement after annealing. That means once its solvent got evaporated by putting thermal annealing, the structure will automatically change. So the thermal annealing also will got impact. At the same time, not all the material, yesterday we heat up to around 100 and 120 degree, but some material it may take 100, some material it may 80 degree, some organic semiconductor will take 150. It depends on, it's not fixed for one material, it should be varying. So the optimization will, you have to do it at various range of temperature and study the performance, which one is giving the good performance. Like this, we need to do different laborious type of work when you have to find the optimum things. And what I'm saying is, just in the previous slide I show that how the composition make changes, make effect on the device performance. This one shows that how the annealing that we have seen by visibly how the structure is changing. Okay. So the third one is solvent additives. Solvent additive means when you make a mixer, we put some of the, this is chlorobenzene is a good solvent mean. We just put some non-solvent. Non-solvent means some bad solvent. Bad solvent means that is the material doesn't dissolve in that solvent. If you use some of the crystallization, no, we dissolve some material, we then to induce the crystallization we use some of the non-solvent so that we can do the normal any crystal growth, we use the same process. Here also we use the same thing for make the good morphology tuning. Okay. The fourth one is solvent annealing. Solvent annealing, what it is means so like yesterday the chlorobenzene we coat it. Even though we coat it, spin coat it, we get a good film. Still small amount of stray amount of solvent will stay inside the film. Okay. So when you heat it up, the solvent will go out. So instead of by heating force to solvent go out, what you got to do is once you heat it, once you make a film, we just put it in a closed vessel so that we let it very slowly evaporate. Okay, when it slowly evaporates, the film is very slowly aligning themselves. That also makes some difference. That's called solvent annealing. The solvent, we let it evaporate very slowly. When you put on hot plate, we are inducing to go out fast. Instead of allowing fast evaporation, we do the slow evaporation. That's called solvent annealing. Okay, that's one of the process. Another one is solvent vapor annealing. What do you mean by solvent vapor annealing? What is the difference between the solvent and the solvent vapor annealing means? As I said, the solvent annealing, we make a high boiling point, we just leave the film on the closed environment, that is solvent. But instead of closed environment, we put the film inside some solvent vapor environment. We put, for example, the chloroform and tetrahydroform THF is very easily evaporate. We just take a chamber, there we put some THF. Then if you close the things, the THF vapor always will be inside the chamber. Just to put the film inside for some certain amount of time. So then the solvent presented in the chamber will slowly diffuse into the film and it will try to change the morphology. That also has a significant effect to change the morphology of the active layer film. Okay, that's one of the options. That's vapor annealing. The other thing is solid additive. Solid additive, as I said, the same as solvent additive. Solvent means in the blend mixer we add the solvent. The same in blend mixer we add some of the solid. Solid means some of the solid material. What is a solid we will see later. That's all we have. Ternary blend. Now we, by adding third component to the binary blend, then we make a ternary blend, then we can coat it. The third component will help to fine tune the morphology of your active layer. That's why this is a ternary blend active layer. So these are some of the options we have used to optimize, especially the morphology. Why the morphology? To make a perfect bulk junction in the active layer. Okay. So next I said, so origin. Just now I said to make a good efficient cell, three things. One is JC, the second one is VOC, and third one is a fill factor. So the VOC is controlled by, if you have this is donor and acceptor, the if we have this the HOMO of donor is somewhere aligned here, the LUMO of acceptor is somewhere aligned here. So this difference only will give us your VOC. Okay, that's a maximum VOC. Actually, we can't get this one. This is a maximum VOC. You can get it in the solar cell. If you find the energy level of your any donor acceptor by seeing the HOMO of the donor and the LUMO of the acceptor, you can expect what VOC you can get it from the device. If you are not getting that VOC, very less means, that means you are doing something wrong with the device optimization. Then you got to go and optimize device to get the right VOC. So either we got to do interface engineering, or you got to do good extracting electrode or blend ratio, whatever things. But this is theoretically we are expecting. This is a limit for getting good VOC. Okay. So this one we can easily understand by just to find out the energy levels of donor and acceptor material. You can expect what VOC you can get it in your devices. Okay. So for example, in this device we get one polymer and we use a different PCBM. PCBM is C60, BM is a one acetate functionalized one. If we use a BIS PCBM, they have the functionalized two different phenyl functionalizations there. So these two PCBM got different energy levels. One is around 4.2, the third one is around 3.9. If the LUMO is, we can lift it up, eventually you are expected that your VOC should increase, right? As I said, remember, it depends on HOMO and LUMO of the, if you shift the LUMO up, that will add up to the open circuit voltage. So here we are expecting the same thing. By shifting, you can see the JV curve, by shifting this PCBM, for this PCBM you can get the extended VOC. We can see nearly is a 0.2 EV improvement in the VOC, right? Similarly, the another work in BQR PCBM and Y6, you see this one, okay, this is somewhat other concept. There is, yesterday I talked about, this is VOC is some, we can see the difference, but this one again we talk about we have to give enough offset voltage. That is another concept. Yesterday I talked about if you have enough offset voltage, then only you can get good charge separation, then only you can get high performance. Okay. So here I am saying the one example, your VOCs depends on how much the difference between the HOMO and LUMO. Okay. The same example goes here actually. Then another thing is I am saying here the example of different architecture. I said what architecture was using. So this is conventional architecture, this is inverted, and this is tandem. So in the conventional cell, if you use P dot and moly oxide, the whole transport layer as a bottom, the top layer either calcium or PFN. If you put slash means either you can use the PFN or calcium, not two together, either one of them. So either two, because this PFN is a solution process, the calcium is using thermal evaporator. Where both are different processes we use. Okay. If you use a whole transport layer in the bottom, this is called conventional architecture. That means we can extract the holes from bottom side and the electron from top side. But inverted side, by using zinc oxide, we know that zinc oxide is a electron transport layer, so that this one modify the ITO into cathode. So we can, instead of holes, we extract electron from the bottom electrode, and molybdenum oxide like this is P-type, the P-type holes we can get it from top. So just by inverting the interlayer, where we are putting the interlayer, the charge extraction will be according to that one, because that one will facilitate the extract the charges. The interlayer will tune your electrode, then they change the work function. That will make the change of built-in function between this one. That will help to extract electron from the bottom side and the holes from the top side. Okay, just changing the interlayer, you can change the architecture. So this tandem structure we can use. As I said, is a stack. We use two cell in one stack. So here we use usually we use a wide band gap material as a bottom side, your cathode interface layer and active layer. In between you have the interconnecting layer. Interconnecting layer is nothing but if it is a cathode is anode and cathode together, then we coat another layer, then anode material. Finally, we will get only two electrode system, only connection. But when you add this stock, what will happen is the voltage will get added up. Suppose in case if this is giving 0.8 volt, when you connect this stack layer, the voltage will get added up, we will get 1.6 voltage, so that we can get enhanced efficiency. So when you have the series, this device, like same as what you are getting in any series current, if you use add up, the voltage will get add up, but current will be same. So here the problem is the both active layers should generate equal current. If it is a different current is generated, because of the current mismatch, it may get only take the lower current. What is the things? Okay, we need to make sure that it should generate the same amount of current, because in the tandem device only the voltage will add up, the current will be still stay. Okay, so here the front cell will be take off, other one the VOC will get instead of 0.8 will get 1.6 volt, and we can get a 15% efficiency from this cell. I think now you get the point. How many different architecture is there? So it depends on what efficiency you want. According to that, you can choose. Okay. But for in practical purpose, for the large area fabrication, we always prefer using the inverter architecture where we printing, because this inverter architecture is using more stable than regular architecture. Okay, so this is some of the material designs so far and giving the efficiency. This is one of the PBDT-PT is developed in our lab in Melbourne, giving 9.4 and PT by 7 TH and other. These are I'm giving some of the different material. What is a performance of this material? These are all developed before 2050. Okay, and this is effect of interlayer. Just now I saw that the interlayer, according to interlayer, we can make you said conventional architecture or inverter one. This is some of the conventional architecture. Not only P dot, which is a whole transport layer, and we can replace a P dot with the nickel oxide, because P dot is mainly water-based solvent. Because when you use in air environment, the water get always is a highly acidic material. Sometimes it may not be good because it can corrode ITO, because this is coating on top of ITO. Sometimes this P dot may react to the ITO, and the long-term effect it's not good. So people are always finding what is alternate for ITO, but it's still good. P dot is very good material, very good. It gives very good work function for the whole transport layer and easy to coat. For testing purpose we can use it, but long-term purpose it's not good actually. So people are developing alternative for this one. The one of the alternatives is nickel oxide. It's a very good whole transport layer. So when you see even replacing this P dot with nickel oxide, we can get an efficiency of close, even we can get a better efficiency. Okay, that's why when you make a functional device, we can test using P dot PS initially, but when you go and make a functional device, we can use a different whole transport layer, which make very efficient performance. Okay. In addition to P dot PS, the molybdenum oxide is also another option. People are using as a whole transport layer. So that also giving a decent improvement in device performance. You see, at least we can see the improvement in fill factor. Fill factor is a very important parameter. It will make the device fill factor is improved and the long-term device performance when you have this type of metal oxide. Because one of the advantages of using metal oxide is the metal oxide is highly stable in temperature. At the same time, it will protect the active layer from degradations, because this metal oxide is already oxide. So you can't make it further oxidize this material. Instead, if you use other organic material, it will oxidize the air environment. Okay, so we always prefer metal oxide to make the interlayer. Okay, this is another. I'm just saying that when you do this type of metal oxide, what is really happen? So P dot, we know is simple things we do. When you do moly oxide, we have done this type of. This is very old work in 2010. I did in University of Florida actually. When you have this type of, we make this type of silol polymer material, and we got an efficiency of 4.4. But when you use a moly oxide, using this, when you use a just replace a P dot basis moly oxide, we see the improvement device performance, especially in fill factor. We are at that time we are wondering why the moly oxide is giving this much enhanced performance. Then we go and study with the UPS. I think now you might have said what is UPS is doing. So this is a secondary cutoff of UPS. So initially when you coat this layer, the secondary cutoff is only 7.5. By coating small moly oxide on top of this this material, you see how the secondary electron is shifting. For one angstrom moly oxide is shifting around 0.5. The secondary cutoff. That means the Fermi level is shifting. When you have the 8 angstrom, 2 angstrom, when you have the 6 nanometer, it almost shift very huge. there will be a lot of work function shift, which is favorable for good hole extraction. You can see that. At the same time, this is HOMO onset. That also we can see the difference in the onset of HOMO. Not only the work function shift is there, the band bending is there, but at the same time, it will change the HOMO level of the hole transport layer as well. That will cause us the enhanced performance in this state. So that time we studied this one, we find out what is the reasoning for improvement. Just to change in the work function, what we expected, that is happening when you do this type of metal oxide interlayer, which really help to improve the performance. Okay. This is the one normally, this energy levels. Okay, now we come to this morphology control. First we see that mainly if you want to do the real application of this organic solar cell, we need to have the really develop the material first and do the lot of device optimization. Device optimization involve interface engineering also. This one we will talk about in detail in the last class. The device optimization, one of the concept is, this is active layer optimization, bulk heterojunction optimization. Okay, that means we do the nanoscale morphology of active layer. Nanoscale morphology means is a nanoscale phase separated bulk heterojunction active layer. That means, okay. Then we talk about the stability. If you taken care of all these things, then we can really go for a real application of these devices, from starting from material designs to your application of this device. Okay. So these are important factors. Okay. As I said now, why this bulk heterojunction concept is important. So this is like a domain size, how is it forming? When the exciton is, when the light is fallen, exciton is formed, the exciton diffuse to the interface that's within the 20 nanometer radius interface and gets separated. Then we have the percolated, the continuous pathway for donor to get the holes extracted, and continuous pathway for the acceptor domain to get electron get extracted. So this domain size and domain connectivity and domain packing, everything is important. So this domain size and domain packing is, we can find out, yesterday we talked about the GVAX, that will give this type of information, what is the domains and how is the purity of domain. Okay, so this is one. Ideally what we want is, this is a structure, but this is very difficult to get this type of structure, because if you have this type of anode is connected to the donor, sorry, this is like your acceptor phase connected to cathode, this anode phase connected to the donor with the anode. If you have this type of factor, we are systematically introducing the donor acceptor interface very well uniform distance. Ideally this is architecture we want, get a best efficiency, got at least for 100% one. We can't get it, we are trying to do this one, but this ideal structure. Normally we will be get up with getting this one only. So this ideal structure we want. And also the disordered morphology. Normally it's very difficult to control this type of ordered morphology. We always get disordered morphology. That's why we are getting the little bit very low performance in the device. Okay. So loss factor is for the exciton decay. Sometimes, as I said, 10 to 20 nanometer is exciton diffusion length. Some material can decay fast. Some very good material, the exciton diffusion length is higher. It's settled materials property. Not all the material is only 10 or 20 nanometer. Okay, it depends on material property. And also I said is depends on the mobility of the material as well. Okay. So anyway, between around 10 to 20 nanometer only. So that's why we need to make this type of bulk heterogeneity concept. Okay. So this is one of the example I gone through one, how the morphology control. This is one of the good example for additive, because when you make a blend layer, sometime you will end up this type of very bulky morphology. If you see this one, the size is nearly 0.2 micron, is half a micron size. Actually, we are expecting 30 nanometer, but finally end up with the 500 nanometer. If you make this device, the device very poor performance as what we are expecting this. Okay, so then after adding this some type of additives, this morphology can be fine-tuned to nanoscale morphology. This is a required one. So that's called your additives we can use. Another thing is solvent choice. So yesterday if you see that we use, because I can't use, chlorobenzene is a good solvent for P3ST, but chlorobenzene, you know that all the chlorinated solvent is toxic. Yesterday I tried to use here toluene. Toluene somewhat is okay, say industrial relevant solvent. If you see the toluene, if it is, you can notice that when you heat up it dissolves. As soon as I take it outside, when it cooled down it becomes solid. Okay, some solvent will only good soluble only it takes, but if you dissolve in chlorobenzene, even at room temperature the solution is stable. It won't solidify. Okay, this is solvent property. So different solvent got different property. You can use a right solvent. Okay. Anyway, toluene is good. You can coat the film its hot condition, but when you cooled it down, it becomes solid. At hot condition we make a good film and let it cool. It's a good film. So that's a good concept. But we should not leave it good with the solution itself. But if it is a solution is solid, means we can't able to coat it. But for coating purpose, we need to have a good solubility. But for film purpose, it should be very good solvent, very solid material it should form. So choice of solvent is very important. People use always chloroform. Why chloroform means? Chloroform, you know, that's a very low boiling point. If you leave it in air, if you come back, it will always evaporate. Okay, that's why if you make a film, if you leave it out, it's immediately dry. It will give a very good film. You see, you can see that in naked eye. After making good film, you can get a very good film. But in chlorobenzene, you have to treat it with the annealing, thermal annealing, or then only you can see a good film. But chloroform, you can say a very good film formation. Okay, and this is the one just now I explained to you just now. What is solvent annealing and vapor annealing? So in thermal annealing, just yesterday what I said, I just leave it the film on the hot plate. You can see that how it changes. This is called thermal annealing. The solvent annealing, as I said, the chlorobenzene high boiling points, we coat it. When even after coat it, some of the stray solvent will stay inside in the film. Just put it in the closed chamber. Let the solvent slowly evaporate. When the solvent slowly evaporate, then the molecule get slowly aligned and get a good film. So solvent annealing. Solvent vapor annealing, the difference is here just a film we leave it in the closed chamber, but in this also closed chamber, the chamber fill out with some of the solvent. So when you have the solvent, this solvent vapor should be extended here. This solvent vapor slowly get into that will try to change the morphology of your active layer. So this is a difference between the solvent annealing and solvent vapor annealing, because we externally introduce the solvent inside. Okay, hope you can understand the difference. Okay, now we can see what is the effect of solvent here. You can see if you make devices in chlorobenzene, sometimes we can get a very good, nice phase separated one. At the same time, when you use a toluene, you will use a very bulky morphology, which is not favorable. When you see the device performance, the toluene give a very low device performance, only 0.74, but chlorobenzene give around 1.6, nearly double the time the performance. That because of the morphology is not the right one. The same as yesterday when you put the toluene, it's easily, when it cool down, it easily gets solidified. Already it lost the solubility. Like this, the solvent choice will make the quality of the film differently. Okay, and also the thermal annealing. So after thermal annealing, sometime you can see well separated phase separated morphology. And also if we compare this film morphology, this film will get low performance. And you have the very good nanoscale. You can see the very black and white spot, everything is a well phase separated morphology. This is only 100 means. This will be in the 20 to 30 nanometer, these phases. That give the very good improved in the device performance. You see, the substrate current improved from 3.82 is close to 10 milliampere per centimeter square. So this is the effect of the morphology of active layer film. If you get a very good morphology, you get a maximum performance out of it. Okay, there are various ways to induce this right morphology. Okay, this is thermal annealing. So another one is you can see the different drying conditions. Just now I said when you have the solvent annealing, we just leave it with the different drying. We close it, we let it dry. So when you have the drying differently, you can see how yesterday we saw that the absorption spectra, we can get this solder peak. If you are getting solder peak, means you are ordering the crystal, the film arrangement is very good. That's why we are getting this. Otherwise, if the film is not good, the order is not good, means we just get this peak. You can see the difference of this peak and this peak. If you get any solder peak, it got your active layer film ordering is very good, that you can see that. Okay, and you can see that the 7 option, 1 or 2, they get a best performance of, the best performance coming from when you get this type of soldering, number 1 is giving the performance of 4.37, but rest of the things is very low performance. Okay, this is coming from solvent annealing. This example is for solvent vapor annealing. So this device is coming from my lab actually. So we make this material and study that when you make normal device, we said only give 5%. We are expecting this material should perform high, so that we did some of the optimization. We follow this solvent vapor annealing technique. So what we did is we coat this blend of BTR and this material in the PCBM and let it in the solvent is, we tried all type of solvent, chloroform, CO, CS2 and THF. We found that when you put solvent THF inside, that will really change the morphology of things. Then the performance went up from 5.2 to 9.3% here. Okay, this one. So again, we see that what is really happening means we see that the solvent is when you have the 22nd only solvent blending, the morphologies really have the very fine nanoscale crystal is forming. So that's why the performance going up to 4.6 to 9.3. But again, this is only after solvent annealing. We try to heat it up the solvent, but that makes the performance very rest, because when you do both vapor annealing and thermal annealing, it again reverses the process. We have to do either one of the process to get a right optimization. Okay, so this one will shows that just try to different. If you see this one, this donor and acceptor, we have the Thiophene unit of 1, 2, 3. It's this called we can put the term T is ter, only the 3 Thiophene. So we increase the Thiophene from 3 to 4. Now if you see this one 1, 2, 3, 4. If you increase the Thiophene, it means we are increasing the conjugation. If you increase the conjugation, what will happen? That will change the band gap. So extended conjugation will decrease the band gap. We saw in the first class. Okay, the designing. That's what we are expecting here. When you increase the conjugation from 3 to 4, the band gap is decreased from 1.97 to 1.8. Just for 1 Thiophene will decrease the band gap. That will improve the performance from around 9.3 to 9.4. The best thing is, even if you do the annealing, the device is still stable. The extra Thiophene not only improve the performance, it will improve the thermal stability, because of course when you make a device, it should be stable for when you heat it up. But when you have this extra Thiophene, here it really helpful to improve the stability. And when you study this photoconductivity, you see at a very low voltage with the solvent building, the device with the vapor annealing, we have very good extraction of charges, photocharges, whereas this device is still extracting the charges. And also if we study the photocurrent versus voltage, we can get this is a slope is nearly 1 for the device with vapor annealing. This shows us very good reduced bimolecular recombinations. That's why we are getting a very good fill factor as 72%, 70 in this case. So if you make a very good material with the right optimization, you get a very good fill factor and a good performance. Okay. So next thing is, I'm saying that so far we have seen that solvent and vapor annealing. This is solvent additives. Solvent additive means in this case what we are adding is we take a diiodooctane. Diiodooctane means is a C12 chain with the iodine at the end of the thing. This is one of the one liquid. Actually is solvent diiodooctane. We add in the active layer. Take this active layer, mix with the DTS, BTD and the PCBM. Not a very small amount of like 20 or 30 microliter. For 1 ml solution, we use only 30 microliter of this solvent. That will change the morphology is very huge. So if you are not adding solvent, like I saw before that, it giving the very good 500, very big domain of morphology, which says not good. When you have this type of morphology, we are getting the performance only 2%. So when you go to this morphology, what it is giving is the performance go up to close to 8%. You see how much huge difference. Okay, this is we are getting because it's almost we can say 200, 300% improvement in the device performance. No, it's not 200, is a 4 times improvement in the device performance. That means, that's why what I am coming to say this, the device optimization, get the right morphology is important. So whenever people make just to mix it, you do the device, not your job is over. You need to check up, are you getting right morphology? Sometime it will work with the vapor handling, sometime it will work with the solvent handling, and some cases it work with the additives. Which method you choose? That's why the optimization is a huge laborious process. We need to patiently wait and find where is your sweet spot. The finding the sweet spot is very important. That will have, we need to have a lot of patience to find the right things. Okay. So in this case, it worked for just adding the small solvent. You can see that. And also we have studied some of the inverted architecture. We get a very good performance of a 9%. So this work we published in 2011. That time it is one of the very great performance in 10 years, 12 years before. Okay, now we see that this is solvent. The other one is a solvent additive, solid. That is a solvent additive. So instead of solvent, we can also solid material into the third solvent. So that is another option. So we have add this type of, this is a solid material, fluorinated. Here we are trying to say the fluorine 1, 2 fluorine and 3, 4 fluorine to add this type of donor acceptor material. So he see what is going to happen. In this case, by adding different this solid additive, we can see the improvement device performance from 15 to 16.4%. So this will solid additive is slightly little bit changing the morphology, changing the absorption of the spectrum, and is changing slowly the redshift, and also the not only the efficiency improvement in this case, and also this stability also greatly improved for the device with the 5 of things, this type of additive molecule. Okay, and in addition to that, what is really happening means when you get this solid additive is an extra component. So it will only help to change the morphology. Once you change the morphology, it will automatically escape from the active layer. That's one of the good observation. If you see this one, if you add the additives, it will align the morphology the same thing. Once you anneal it, the additive is gone up. It's not stay inside. Okay, but if it is stay inside, then the performance is very low. Okay, we have to choose the solid additives. It only help to induce the good morphology, but the additive should not stay inside, because if the additive would stay inside for longer term, it will kill your devices. So we need to choose additive as a very low boiling point. That's why after making film, when you do annealing, only it will arrange the morphology. At the same time, your third component will evaporate out, and only the active layer stay out. So this is one of such type of additives which give the improvement in the device performance. Okay. So there are some other material also is available which have the same effect. So this one we published in last year. We used this type of tetraphenyl fluorophosphine material to induce this making good material. Okay, we have used this type of architecture to these things, and we got an efficiency of 6 points, close to 7%. When you use the additive was around 10 milligram one. Okay. Okay, and we also see that and with the different additives we can get a very good morphology. At 10 milligram per ml, this is a right morphology where we can see that very good nanoscale phase separated morphology. Even though other things are good, here we can get the right morphology of what we require. So far we have seen all those options, how we can change all those things. So in this lecture, you at least you understand that what are the different options available to make a best cell. I said starting from design, and next is architecture, and talk about interface we will be seeing again. And this one just how to make a very good bulk heterojunction active layer. Why bulk heterojunction is important? Because the exciton diffusion length is very too low. To tackle this one, we have to make the heterojunction very close together. We make a bulk heterojunction. How to bulk heterojunction? There is a lot of different options available. And we have seen all the, there is one more thing, ternary blend is there. We will continue in the next class. In addition to ternary blend, I am going to discuss in the next class what is best device and the current development in this one, and how we can make a large area device. What are all the um, what are all the infrastructure or printing method is available to go from lab scale to large scale printing. So that's one of the important aspect of this one. How we can go from, because I have show you some of the flexible devices. So how we end up with the flexible devices, what instrument we need to use to get those type of device. So far you get know where we are starting. We are starting from small molecule. That means we are starting from acetylene onwards, from how we make a complex molecule, then how we make a device, and finally come up with how is a good device. I think that type of link you should get from this lecture, because organic lectures not only limited to OPV device. Similarly, there is a lot of other devices. OLED, OFET is there, but at least I need to make sure in full depth, at least one device, how we can go from start to point, because this is very short course, only 5 days we are doing. At least I want to make sure that one device fabrication in full way, so that you can take other things, you can export other things by your work. Everything is same, only the material is different, but the process, everything is same. Okay, we'll complete this whole device fabrication process in next class, that is tomorrow morning. Okay, thank you. If any question you can ask. Yeah. Additive, we should choose additive relatively lower boiling point, so that it's after making very good morphology, when you annihilate it's go out. If additives stay inside for long term, it's not good. Yeah, solid is also the same. Yeah, the chlorine interaction is made. That's why I said in this one. So when you add this additive, this is the blue color is additive. So when you add this type of random orientation, the additive helps to make a regular arrangement. After that, it go away when you operate. The additive helps to. Yeah, that's why I choose some additive as a slide relatively low. What means it should be not 50 or 100. It should be around 150 degrees something, 150 to 200. So. At least some interactive. This is fluorine cyanide group. So we have this acceptor also. This interaction fluorine is there. So this acceptor itself will interact. Yeah, in this case cyanide one. There is one more case. We have used fluorine. So the interaction will be different. That we need to find out. There's a fluorine. Both cyanide and fluorine get the same effect. It's acceptor effect. That is the N layer. Yeah. That is only the bilayer device. Now we are shipped to already the bilayer device too. No, here that one doesn't apply, because that's only for N layer is too small, means because that time the exciton generation happened only P type. The exciton should come to the heterojunction, so that if you want to, if it is its diffusion length is only 20-30 nanometer, the layer should be within the 20-30 nanometer. Then only it can come to heterojunction. Otherwise, the exciton will recombine and you cannot generate any charge. That's why in bilayer device, the device performance is too low. If you say the short circuit only that 1 or 2 milliampere. Okay, but in this case, if you have the same thing, bulk heterojunction, the 2 milliamp will go up to 8 to 10 milliamps. That because you increase the heterojunction in the active layer, that will help to charge generation is more, because your exciton is really get dissociated and charge got separated. Yeah. Hypothetically depend. That's the one, because when you have the heterojunction, if your heterojunction is regular, that's a really we want. That's we theoretically define. But you're trying to do the practically like what you said, there is a block copolymer donor acceptor next space, but still can't able to fine tune the similar architecture. Sometimes when you generate the architecture, the mobility gets different. Okay, we have to get all the properties in one guide. We have to get good architecture at the same time. We should not sacrifice mobility. When you do all this material, the mobility is too low. Which one? Yeah. there is no report with the good architecture with the high performance. They reported have got order structure, but the performance poor. There is some other factors involved. Yeah. Any question? Yes. Yeah, of course we get a very less external dissociation. The current generation is very less. Now we are getting a very good performance. The current of 25 milliampere. We will get less than half of the things. Less means no. There is not efficient exciton dissociation, because exciton, the bound charge, it should get dissociate, separated charge, then only charge flow, right? If it is not separated, the charge cannot be generated. Correct. That's the main thing. There will be a lot of initial thing is that we need to separate the charge out from the exciton. That's the main thing. That's how we do bulk junction. Yeah. 24, right? This. No. This is a big donor means if this is donor phase, this is acceptor phase, or if you donor this acceptor. Donor and acceptor, that's what I said, right? If you want to get the exciton separated out, the domain size within 20-30, that is the exciton diffusion length is 20-30 nanometer. You diffuse 30 nanometer, when you reach the heterojunction, it gets separated out. In this case, it's around 500 nanometer. It's very much larger than the exciton. So the charge not dissociated, it's get recombined. We are not getting enough charge separation, the exciton dissociation. That's why low. The current is very, very low here in this case. So still we are getting current, but in this case, the exciton is generated here, or sometime it may get generated at the edge. Those things generated at the edge can separate out. The exciton generated at the middle cannot come to the heterojunction. That's why we are not getting enough charges. But at least some charge is coming. Yeah. That's why we go from here to here. Very small domain. All the charges all the exciton get dissociated. Any question? Okay, now it's 11:10. Next session should be, so if it is no more question, so we'll go for a demo for CV and some of the electrochemistry aspect. Okay, the rest of things I will complete in next class, and even if you think of any question, you can ask me tomorrow. Okay, thank you all. Okay, after the break, we go for demo.